Hi, folks. Welcome back. I hope you're all doing well. So, one of the most common arguments that the AI doomers have is that the models can never get smarter or better than the data they were trained on, and hence they will never surpass the level of humans. At the same time, there have been plenty of anecdotal reports on Twitter, on the web, all over the place, where human experts at the PhD level or above, people that are professors at top tier research universities, have been surprised by the things these models have been able to tell them. So we already know that these models can at least meet the level of and sometimes surprise the people who would be considered to be the elites of their field. And this paper, which came out just last week, was really interesting because, first of all, it gives this phenomena a name. They call it transcendence. And second of all, they actually look at the underlying mechanisms via which transcendence happens. So let's go through it. I really think that this is a very well written introduction. As they say over here, the model is not a person, it is not even trained to mimic a person. It has been trained to mimic a group of people with individual capacities, predilections, and biases. And then they give this thing a name. Our goal is to describe how a model trained to mimic multiple people is capable of transcending its sources by outperforming each individual. Essentially, they're saying that the whole, the model as a whole, is greater than the sum of its parts. And how does that happen? What are the underlying mechanics at play? So, not to bury the lead, the three main mechanisms via which transcendence happens are: number one, skill denoising. This is basically a fancy term for wisdom of crowds, which is to say that you poll all the best experts on a given topic and you average out their answers. This is very similar to the main point of this book from 20 years ago, published in 2004, The Wisdom of Crowds by James Surowiecki. This is the book that popularized the phrase the wisdom of crowds. The main caveat is that when you ensemble these experts, the experts must have been not correlated. So this only works if each expert came up with their judgment independently of all the other experts. As they say over here, each may make independent errors. So that's the first mechanism. The second mechanism is what they call skill selection, which can be essentially thought of as routing to the appropriate expert. When a general model gets a query, it should be able to then find the appropriate expert within it to route that question to. And this makes it look like the generalist model has the union of all these fields of knowledge. And then the third one is the most fascinating one, which is skill generalization. So note that the first two methods, skill denoising and skill selection, still only work over knowledge or wisdom gained from the training corpus. Generalization goes beyond what was in the training corpus. When you take what was given to you in the training data and can then either extrapolate or reason or compose that knowledge in some way to come up with a new fact or a new conclusion, that is skill generalization. And this is something that would be truly new. This is a piece of knowledge that the individual experts within the model or the individual experts within the training data would not have known just by themselves. Then the rest of this paper is about how would you construct an experiment and a model that demonstrates these three mechanisms at play and the magnitude of their effect. The way they set it up is as an inference problem over a given knowledge graph. A knowledge graph is a graph where the nodes are concepts or entities, and the edges between those nodes are the relationships between them. So you can see a very simple knowledge graph over here. These two nodes are siblings, so the edge is labeled sibling, for example. And they call the facts that join nodes with one edge one-hop facts. So this is a direct relationship between two nodes in the knowledge graph. And then you also have what they call two-hop facts, where you have to join not just one direct relationship, but two direct relationships. And when you have two-hop facts, you can have two kinds of two-hop facts. So within a knowledge graph, you have this notion of expertise within a field of knowledge, and they show it here with these two colors. You could combine two relationships within a single field of expertise, and that's called a two-hop fact within expertise. But you could also combine relationships that cross expertise boundaries, and that's a two-hop fact across expertise. And they build a synthetic knowledge graph with completely made up names and relations so that there's no danger of the model, the base model, having any existing world knowledge of these things. And they set up the experiments with a fine-tuned version of GPT-2. And then what do they test? They basically test for predicting these entity relationships. So given a node, a relationship, and then another node which it is related to, you basically strike out the tail and ask the model to predict the node that is struck out. So this is the limited experiment that they set up to see how these three mechanisms play out. And maybe this is the best they can do because obviously they're not inside the big labs. They don't have access to the weights or the training of the latest models like GPT-5 or Gemini 2.5 Pro. But the point of the paper is that since they demonstrated these things working in a smaller model, the idea would extrapolate to today's larger models as well. And let's look at the first idea, which was skill denoising or aggregating expert knowledge. And what they find is that as you increase the number of experts, the model can substantially outperform individual experts. And what numbers did they get? The model achieves over 80% accuracy when trained with 100 experts, even for expert coverage scores as low as 0.2. And so these experts were noisy. So if you have experts that are diverse, they have uncorrelated errors, the resulting model is able to perform at a much higher skill level by using an ensemble of all their expertise. Now, when it comes to skill selection, you have this interesting problem that how do you tell, just by looking at the training data, which expert should be judged as an expert on what topic? How do you know what somebody is an expert on? And the way they're trying to set it up is they construct the training data in a way that experts talk more about the topics that they are experts on. And that's the main criteria they use for skill selection. So if you have training data for an expert on topic X, that training data would mostly be talking about X and not about other random topics. And this works out as well because what they found was as the number of experts grows and experts have this swim in your lane property that they talk about their own expertise, the model can achieve high accuracy even when each individual expert knows only a fraction of the knowledge graph. So this is good data to back up the second mechanism, expert selection. And finally, we come to skill generalization. And this is interesting because this is something where you're trying to arrive at a fact or a piece of knowledge that no single expert knew in the training data. The model must compose knowledge from multiple experts. The way they're trying to measure this is by looking at how well the model does on coming up with two-hop facts that are cross expertise. These were held out during training, so the model would have to deduce these. They didn't use GPT-2, they used a 1 billion llama model. And here they had to push a bit harder. They had to allow the model to use chain of thought to get higher than 60% accuracy on cross expertise two-hop queries. Essentially, they're using chain of thought to rephrase the problem, and that's how it finds the facts that it must compose over. So this was a quick look at a paper that details the mechanisms, that names and details the mechanisms via which models can perform better than just their training data. Skill denoising, skill selection, skill generalization. And then they show in a limited setting how these mechanisms play out and how they actually work. And they do seem to work. I hope you found that helpful. If you like content like this, please like the video, consider subscribing, and I will see you next time.